Good morning. My name is Miquel Garcia Ratés. I work at Facts, and today I'm going to talk about the new features regarding implicit solvation in ORCA 6.0. In this context, several changes have happened since ORCA 5, ranging from new implicit solvation methods, new way to treat the solid cavity, as well as changes regarding Hartree-Fock, density functional theory methods, and post-Hartree-Fock methods. The first point I want to talk about is the way the input is processed in ORCA. Well, this is a spoiler, but in ORCA 6.0, we have 6 different implicit solvation methods. 2 of them, CPCM and SMD, are natively implemented in ORCA. Then we would have the methods available within XTB, ALPB, DD-Cosmos, CPCMX, I will talk about later. And finally, the interface of ORCA with OpenCosmos. Well, there are some disadvantages there in ORCA 5.0. For instance, for CPCM, we only have about 20 solvents in our internal database. And the epsilon for the solvents is not fully consistent. It sometimes corresponds to different thermodynamic conditions. The SMD model, on the other hand, has many more solvents, almost 180, but it's not very easy to call, to request. We have to always add these 4 lines. So on top of these disadvantages, drawbacks, I would also add that if we have a solvent that exists in different solvation methods, it may happen in ORCA 5 that the solvent input name is different. So we don't want that. We want some sort of homogenization there. So all these points have been fixed in ORCA 6.0. What it's done there, ORCA would process the input file, scan it, and after that, a set of unique identifiers per solvent, an ID and a string, are generated. After that, based on these identifiers, the solvent data descriptors are set up and the calculation would run. For instance, for acetonitriol, we would have these 3 possible input names, but at the end, ORCA, no matter which is the solvation method, would produce this unique string. So what has been done for CPCM? We have increased the number of solvents to 182. This covers all the solvents available in XTB, in SMD. And now the epsilon is that at room temperature, like 20 degrees. This is different than what we have for SMD, where it's 25 degrees. This is the temperature it was parameterized. So now the epsilon for CPCM is fully consistent, with the exception of ammonia, whose boiling point is very low. As I say, we have a unique ID and a string per solvent, and this is the same for the rest of solvation models. This would be a snapshot of the output block for CPCM in the ORCA output file. Here we would have the epsilon, that now it's a bit different than that for ORCA 5.0 because it may correspond to slightly different conditions. So one has to take that into account in case one wants to reproduce the data that you had before. The input string is now printed here, and for water or H2O, we always would have water, okay? So if we change epsilon or the refractive index of the solvent, then the solvent is custom because we are customizing it, okay? For SMD, what we have done now is we have a new way to request it. We can do it via the simple input. We just need to write SMD and the name of the solvent. This contrasts with what we had in ORCA 5 or what we have to do now via the CPCM block. This is still doable, but it's much easier to do it via the simple input. And this strategy extends to the rest of solvation methods. That is CPCM, ALPB, DD-Cosmos, CPCMX, CosmosRes, okay? So we can say that in ORCA 6, it's very easy to request any solvation method. So here there is a snapshot of the table with the possible input names for the solvents with the different implicit solvation approaches. So for instance, for dioxane, we have 2 names, and we could write any of them, no matter if we use CPCM, SMD, CosmosRes, ALPB, or DD-Cosmos. Okay, this is really an advantage. Okay, the next topic I want to talk about has to do with the solid cavity and the way it is discretized. In ORCA 5.0, for the Gaussian charge scheme, we use a constant number of levered points per element, independent of which element we are considering. This is 110 by default, and we can go for different discretization levels. But as we see here, for instance, for 770, we can see that the charges around the hydrogen atoms, you have a larger density than for the other elements here. And this is something we have improved in ORCA 6.0, where the new default is the so-called isodensity scheme, where you have a constant density of charges per unit of area. The default is 5.0. And here we see situation that corresponds to the default. So you see the density is much more homogeneous. If you go for 10, you would also have this homogeneity there. It's not broken. So how to request it? We have two thresholds, one for hydrogen atoms and one for non-hydrogen atoms, the defaults being 5.0 for both. But we can increase the one for hydrogens, for instance, here, and we see that the density is larger than here. We have new available level depth grids that extends for both schemes. And one thing is that for the new scheme, you have more charges than before for ORCA 5.0. But this is really not a disadvantage because you have more accurate results. I mean, for heavy elements with larger radii, you have a better treatment of the density of points around your element. And at the end, the integrals in ORCA 5.0 was lower than in ORCA 6.0. So the computational cost will be still faster than before. But if you want to reproduce the results you had in ORCA 5.0, you just need to specify numleb and the value that you had. Okay, so let's talk about a new feature regarding the treatment of the solid cavity, which is new in ORCA, is the dynamic radii adjustment for continuum solvation, DRACO. This model has been developed in the group of Professor Stefan Grimme in Bonn, and the idea behind it is that the radius of the elements in the cavity reproduce the state of this element and which is the surrounding of this element, okay? So what you have is that the original static radius is scaled by a factor to produce the so-called dynamic radii. The scaling factor depends on some element-specific parameters, but basically on this effective partial charge that for each element depends on the atomic partial charge, which in our case we use the electronegativity equilibration charges, and the coordination number, which we have the one used in GFN 2XTB. So this model is available for CPCM, SMD, and 4 different solvents. And from the paper, we can see that the mean absolute deviation for free energies of solvation decreases to up to 5 kcal per mole for a large set of neutral and ionic systems in CPCM, 1.5 kcal per mole for ionic systems in SMD, and 0.2 for neutrals in SMD. Right now, it's only available for single point energy calculations, but in the future, we will extend that to the gradient. And it's very easy to request via the simple input or the CPCM block. Okay, the next topic I want to talk about is solvation in coupled cluster methods. Well, in ORCA 6.0, we have fully implemented the most elaborated scheme we have there, the perturbation theory energy for singles, for canonical and DLPNO CCSD. This is the new default. And this is available for closed shell and open shell systems for the energy. And one can also request and relax densities, let's say compute dipole moments with the CCSD density. We have also fully implemented one level lower or below the PTE parentheses S scheme. So in ORCA 5.0, this was not the default, so we had to specify CPCM CCM2 in the input file. And now we don't have to do anything since it's the default, only requesting DLPNO CCSD or canonical CCSD. The same for SMD. But here, some warning for the users. Be aware that in ORCA 5.0, the default is the PTE scheme, the simplest one. So if you run 2 calculations with ORCA 5 and 6 with the defaults, be careful because this does not correspond to the same situation. Okay, the next topic has to do with charge compensation and vibrational frequencies. Here, in ORCA, well, in implicit solvation methods where you have a cavity, many users may know that there is a fraction of the charge of the solute that may cross the cavity and escape the cavity. This is called the outlying charge effect. In ORCA 6.0, we have implemented a Lagrangian-based algorithm to compute that correction to the charges. And what we have finally is the corrected charges that depend on the original ones, plus a term that depends on this Lagrange multiplier. We also have a correction for the dielectric energy. And this is printed in the output. Here we would have the surface charge that escapes the cavity. And here the corrected charge after applying this algorithm. And this is the correction for the dielectric energy. Together with that, we also produce a file with extension CPCM core, where that contains the corrected charges. But here I would just want to remind that this is something that we don't consider for the SEF energy and derivatives. It's only for printing purposes, in case you want to use these charges for some workflow. Okay, next topic. This is an important feature that users will really like, has to do with SMD. In ORCA 5.0, the SMD is available for single-point energy calculations, geometry optimizations with the analytical gradient, and for the Hessian, we need to compute the Hessian numerically. Then this SMD is also compatible with the rest of methods in ORCA. But as I say, if we want to calculate frequencies, we have to wait quite a bit because for a large system, the numerical Hessian takes some time. So what we have done now is implementing the analytical Hessian for SMD. And what is done there is the electronic part is done analytically, let's say the one that corresponds to CPCM, and the cavity dispersion term is computed via finite differences numerically. And now you can request the analytical Hessian in SMD. So this is something that will make your calculation faster. Okay, as you know, in ORCA, we also have solvation in semi-empirical tight binding methods like XTB and QMMM. What have we done there? Well, for XTB, in ORCA 5.0, we had the analytically linearized Poisson-Boltzmann model. Now we have two new methods, DD-Cosmo, domain decomposition Cosmo, and extended CPCM, CPCMX. DD-Cosmo, the idea behind is basically that for CPCM, but for XTB. So we have a solid in a cavity, and you have a set of charges around the cavity. But here in DD-Cosmo, what you do is you decompose the domain of the cavity in different subdomains, and in each of these subdomains, you solve the CPCM equations. And CPCMX, you do DD-Cosmo for XTB, and after that, there is a post-processing that is done in a Cosmo-RS and SMD way, okay? The idea behind CPCMX is very well illustrated in the graphical abstract of the paper. So for ALPB, you would have the results quite fast and with a certain accuracy. For CPCMX, the calculation would take a bit longer, only a bit, but the accuracy would be much better. And if you run Cosmo-RS or SMD, let's say quantum chemical methods, DFT or Hartree-Fock, whatever, you have better accuracy, but the computational cost is much higher. So this is the idea behind CPCMX. And these methods are very easily requestable through the simple input or the XTB block. Each of them has a different amount of solvents. Regarding QMMM, there has been some work in Onium. As you may know, Onium, what you do there is you divide your system in a large system that is treated with a low-level method and a small system that is treated with a high and low-level method. And at the end, the energy of the total system is a combination of the energies for these two systems. Well, in ORCA 6.0, you can request these three solvation models within XTB for the low-level calculation. And if you run CPCM, you can, or SMD, you can do it without any problem for non-XTB. So this is new in ORCA 6. And here we have also done something in ORCA 6. Let's see what we have done. So if we have DD-Cosmo for XTB or CPCM SMD for non-XTB, in ORCA 5.0, if we consider the big system, you would have the CPCM charges here, but these charges would not be used for the small system. This is the so-called CPCM-C model. But now the new default, if you specify these settings, is that for the big system, you have the solvation charges, and then the solvation charges are used as embedding charges for the calculations for the small system. This is called CPCMB. And this is the default. If you run ALPB or DD-Cosmo or CPCMX with XTB, you would automatically do CPCM-C by default. Okay, so at this point, we reach the last topic I want to talk about, and that is the interface of ORCA with OpenCosmo-RS. OpenCosmo-RS is the open source implementation of the conductor-like screening model for real solvents, Cosmo-RS, which was firstly devised and implemented by the group of Professor Andreas Klamp and co-workers. And this is a tool that is highly used in the world of academia and industry to predict fluid phase thermodynamics without requiring experimental data. The basic idea behind this method is that it is based on information coming from quantum chemical calculations and a fast model to calculate molecular interactions. In this case, the molecular interactions are represented by a set of interacting molecular surface segments on the cavity of the solid and the solvent. So this would be the solvation free energy, comes from the paper of Simon Mueller and co-workers, which are the people that developed OpenCosmo-RS, and the code is also available via this GitHub because it's open source. But in our case, because it has been parameterized for ORCA 6.0, we will ship the executable with our binaries. But some highlights, the OpenCosmos produces accurate free energies of solvation, around 0.5 kcal per mole deviation with the experiment for a large set of neutrals, and the deviation for the agreement between experimental partition coefficient and infinite dilution coefficients is also very good. Okay, what does ORCA do when you run a Cosmos calculation? Well, first of all, a single point energy calculation for the solid and the gas phase is run. In this case, with these DFT settings. After that, the same calculation is run for the solid in a conductor with the same settings. And finally, we do run a calculation for the solvent in a conductor. After that, information from these three steps is gathered, and ORCA would call the Cosmos executable, the OpenCosmos, and solvation properties would be computed. So this is the workflow, or ORCA runs single-point energy calculations, produces some output files that are processed as input by OpenCosmos. OpenCosmos does the same, produces some output, which is internally processed by ORCA to print some solvation properties. How do we run a calculation with Cosmos? So the easiest way is to use the internal database of solvent that we have in ORCA. So we would just write Cosmos and the solvent, and the geometry of the solid would be also provided. We can also do the same via the Cosmos block. There are 93 available solvents. Another strategy would be to provide our own structure for the solvent, so we can use anything we want. In this case, one has to provide a file with extension Cosmos XYZ, and the name of the file without the extension is provided in the input file. Okay, the functionality within Cosmos can be specified in the Cosmos block, but all these parameters are special for ORCA 6. So in principle, unless you really do know what you're doing, it's advisable to not change these parameters. So let's see an example how to run a calculation. This is the case of acetone in water. So we would have Cosmos water. Water is loaded from our database. And the first thing ORCA does is to print information regarding solid, solvent, and the type of calculation. And after that, the energies of the three different ORCA runs single point energy calculations that I told you before. And after that, Cosmos would be executed, and we get finally the free energy of solvation at the corresponding temperature. So if we want to compute the free energy of a solvated system, what we can do is to compute the free energy of the system in the gas phase. Let's say one run frequencies, thermochemistry, and you add this term on top. And here we can see that the agreement with experiment is very good. So at this point, I'm done with the features regarding implicit solvation in ORCA. I just want to remind you that there is another feature regarding solvation, the solvator, that is a very nice tool to add explicit solvent molecules around your solid. Here would be this Spanish play, and this would be the super ordered, maybe Italian solvent molecules. Okay. Well, after that, this is the highlights of what has been done in ORCA 6 regarding solvation. And after that, I just want to say thank you for your attention and enjoy ORCA 6.